Hi everybody, this lesson is 7.2.1, Confidence Intervals Lesson 1. Introduction. The Pew Research Center conducts phone surveys to gather the opinions of adults in the United States on a variety of political issues. In a February 2017 Pew Research Center survey, researchers asked a random sample of U.S. adults if they approved of the job Donald Trump is doing as president. 39% of the respondents indicated that they approved of President Trump's job performance. For the purpose of this problem, we will assume that the margin of error for the survey was plus or minus 2.5%. So let's see if we can answer the following questions. So estimating President Trump's approval rating. We're going to discuss the following questions, and we're going to see what we think. So, is the 39% stated in the problem a parameter or a statistic? Give a reason for your answer. So, what do we think here? 39% of the respondents indicated, right? But we don't know if 39% of all people in the U.S. Approve of his performance. We only know that 39% in the sample did, right? So 39% is a statistic since it is referring to the sample, not the population. Okay. All right. Do you think the population proportion of adults in the U.S. who approved of President Trump's job performance in February 2017 was exactly 39%? Give a reason for your answer. Well, let's think about this, right? If you take a sample of people and it gives you a particular percent, we would expect that the real answer is close to that, but we don't necessarily think that it's exact, right? So, we could call this, if you recall, sampling variability. Remember, sampling variability is the fact that when you take samples, it's not going to have an exact representation of what you're looking for, right? 39% is probably not the exact population proportion. Okay, so part C. What do you think the margin of error of plus or minus 2.5% tells you about the population proportion? So we haven't really talked about margin of errors, but we're going to start focusing on that term quite a bit, and then you guys will even be able to come up with your own margin of error. The margin of error, you want to think about the fact that this 39% is probably not perfect, but it's correct within some cushion, right? Some cushion. And the margin of error is exactly that cushion. So what this tells us is the population proportion. Remember, that's the real answer, right? That's for the whole population. Is most likely within 2.5% of 39%. Okay, in other words, it's within 2.5% of 39%. So it could be a little bit higher, could be a little bit lower, but it's not more than 2.5% away from 39%. Okay, that's what that means. Okay, so let's keep going here. We're going to talk a little bit more about this margin of error. So even though the p-hat, the sample proportion, remember that's called p-hat. So even though p-hat is a single estimate of the population proportion, We have a name for it. This is called the point estimate. When all you have is a point estimate, that's better than nothing, but of course, it's better if we have a margin of error that goes along with it. Okay? So an interval estimate is a range of values that we use to estimate a population proportion. Interval estimates are centered at a point estimate. The interval is formed as you take the point estimate and you add the margin of error, and then you also subtract the margin of error, and that gives you the interval. Okay, so let's practice identifying that. So let's identify the point estimate. It says, using the information about the poll above, fill in the following tables. Give your answers in decimal form. So let's look at part A. It says, identify the point estimate and margin of error. What's the point estimate? What's p hat? In this last problem, p hat was 39%, right? P hat was 39%. So I'm actually not going to write it as a percent though, because we are used to writing it as a decimal. So I'm going to write it as 0.39. The margin of error is 2.5%. And so just to remind everybody here how you convert to decimals, you actually move the decimal point back 2 spaces so it becomes 0.39. So if you have 2.5%, if you move that back 2 spaces, you get 0.025. So the margin of error is indeed 0.025. Okay. All right, so let's keep going. The point estimate and margin of error can be used to construct the endpoints of the interval estimate. Give the lower and upper limit of the interval below. So the lower limit, you get the lower limit by taking the point estimate and subtracting the margin of error. And you get the upper limit by taking the point estimate and adding the margin of error. So let's go ahead and do that, right? So what would p hat minus e equal? P hat minus e would be 0.39 minus 0.025. So if you subtract those, what do you get? You get 0.365. So that's what we put inside this box, 0.365. Okay. Now let's do the other one. What happens if we take p hat and we add the margin of error to it? This is taking 0.39 and adding 0.025. And then we end up with 0.415. That's going to go right here. Okay. So we got an interval from this, right? The interval is from 0.365 until 0.415. That's the way you want to look at this. Okay? This is called an interval estimate. Let's move on. So interval estimates like the ones in question 2b give a range of values that usually contain the population proportion, which in our example is the proportion of all adults in the US who approve of President Trump's job performance. So how would you analyze this? Or how would you answer some questions with this? Well, let's suppose that somebody looked at this data and then made the following claims. So suppose a politician had stated that the true population proportion of adults in the US who approved of President Trump's job performance in February 2017 was as high as 50%. Would her statement be supported by these statistics? Okay, so this kind of thing happens all the time in politics where somebody makes a claim after they look at a study, the results of a study, but we have to decide if they're telling the truth. So, if a person says that President Trump had a 50% approval rating in this month, would we agree that that's possible? Well, given that we have an interval from 0.365 to 0.415, 50% does not belong in there, right? So no, the evidence does not support this claim. Since 50% is not between 0.365 and 0.415, right? So again, this is, if you want to look at this as percents, this is 36.5% and 41.5%. So another way to look at it is that the real answer most likely sits between those two numbers. Now again, we're not saying that it's impossible for his approval rating to be at 50%, but we have evidence, and the evidence does not support that, right? So if you're saying something like that he has a 50% job or approval rating in February 2017, this is not based on this evidence, right? So the correct question to ask would be, well, where is your evidence for this? Because the evidence does not show that. So let's move on. Suppose a politician had stated that the true population proportion of adults in the U.S. who approved of President Trump's job performance in February 2017 was as low as 37%. Would her statement be supported by these statistics? So let's see, is 37% between the two numbers? The answer is yes, right? Because it's a little bit bigger than 0.365. So, yes, 37% is contained within the interval. Okay, so any number between those two numbers is a reasonable guess, right? Because that's the whole point of an interval estimate. Okay, let's keep going then. We are now going to learn the correct terminology for this interval. Okay, we call this a confidence interval. So let's read about confidence intervals for the population proportion. We call the interval estimate for a population parameter a confidence interval. To construct a confidence interval, we need two things. First, we always need a point estimate. A statistic is a point estimate, okay? So in this last problem, the point estimate was the actual percent of people that approved of President Trump's job performance in February 2017. So remember that number was 39%, right? So it was 0.39. So that would be the point estimate. And then we also need a margin of error, okay? These are the two things we need. And just to give you guys the symbols for this one, we use p hat for, and the margin of error is the letter E. So then, after you have the point estimate and the margin of error, you always add, so a margin of error is subtracted from and added to the statistic to find the endpoints of the confidence interval. A simple formula for the confidence interval is the following. You take the point estimate and you write plus or minus the margin of error. Okay, plus or minus just means that we subtract it and then we also add it. And that gives you two numbers, right? One's going to be the lower part, the lower limit, and the other is going to be the upper limit. Point estimates, such as sample proportions and sample means, are easy to compute. We have already practiced computing sample proportions. In fact, remember, that's what we did with the M&Ms before, right? As long as you know the number of successful things inside of your sample, you could just do a division and you get yourself a sample proportion. To compute a margin of error, we have to think about the sampling distribution of all sample proportions from a given sample size. Okay, so in other words, we already know how to find a point estimate, but what we need to learn is how to get that margin of error. And that's where we're going. Okay. Next steps. To learn about margins of error, let's think about sampling distributions of sample proportions. In a previous lesson, we examined sample proportions of M&Ms that are blue as estimates of the population proportion. The population proportion is P equals 0.24, but sample proportions vary. We learned that the mean of the sampling distribution of sample proportions, mu sub p hat, is the population proportion. So for blue M&Ms, remember the real answer is 0.24, and that would be the mean. Okay? This means that if we were to take lots and lots of samples, every possible sample, the average proportion of blues that you would get is 0.24, right? But of course, what you get in each individual sample varies from that. The standard deviation of the sampling distribution of sample proportions, sigma sub p hat, is called the standard error because deviations in estimates are errors. The formula for the standard error, recall, we learned this in a previous lesson. It's sigma sub p hat, which is equal to the square root of p times 1 minus p divided by n. For example, let's say you were doing gathering samples of M&Ms of size n equals 50, okay? Then what would be the formula for the standard error? So the formula for the standard error would be, you just take the square root and you write 0.24 times 1 minus 0.24 in there, and if you put that in your calculator, you get 0.060. Okay, so that's how you find the standard error. Okay, so far so good. We already knew that. We're just reviewing some information that we already know. Okay, so let's go on. Try these. Remember, we talked about the criteria for approximate normality last time, so let's do a little review here. We can check the values of np and n times 1 minus p for approximate normality. These quantities are the expected or mean number of successes and number of failures in a sample of size n, right? So in other words, if you multiply n times p, then that actually gives you the expected number of successes in that particular sample. And n times 1 minus p gives you the expected number of failures. However, this is the important fact here. When you're doing problems in reality, the p is unknown, right? How can you multiply n times p if what you're trying to do is find p? So you can't calculate these directly. So instead of checking the expected number of successes and failures, we instead check the actual number of successes and failures in the sample. Okay? All right, so when np is greater than or equal to 10 and n times 1 minus p is greater than or equal to 10, the criteria for approximate normality are satisfied and a distribution of sample proportions is approximately normal. Let's use the normal distribution to distribute the sampling distribution of sample proportions. So first, for a sample of n equals 50 M&Ms, are the criteria for approximate normality satisfied? In this case, we do happen to know that p is 0.24, so we can just calculate directly. Okay. What are the expected number of successes? It would be n times p, which is, remember, n is 50 and p is 0.24. So if you multiply 50 times 0.24, you get 12, right? Do that in your calculator and you can see that you get 12. What are the expected number of failures? If you do n times 1 minus p, you get 50 times 1 minus 0.24, which actually gives you 38. By the way, we could have also just, subtracted 50 minus 12, right? Because if there's 12 successes, then the rest of them have to be failures, right? So that's where we get 38 from, because there's 50 M&Ms altogether. In other words, if we expect to get 12 blues, then we know we expect to get 38 non-blues. Okay, and notice that these are both bigger than 10, right? So what does this mean? This means the criteria for normality is satisfied. The empirical rule tells us that about 95% of a normal distribution is within 2 standard deviations or errors from the mean. Use the mean and standard error from the blue M&M's example to give the interval which contains approximately 95% of sample proportions. Okay. So what this means is that if we just calculate 2 standard deviations away from the mean in both directions, remember this means that 95% of the time that's going to contain the real answer. So let's go ahead and figure that out, right? So what would 2 standard deviations equal? Well, if the standard deviation is 0.06, then what would 2 times the standard deviation be? So 2 times the standard deviation, if you multiply that number by 2, you get 0.12. Okay, so what this means is we need to go in either direction that much, right? So if we started off with 0.24, and if you do 0.24 plus, let me do the subtraction first, okay? First, we're going to do minus 0.12, and we get 0.12. And then if you do 0.24 plus 0.12, you get 0.36. Okay. So this is the interval that we're talking about. We're going from 0.12 until 0.36. What does this mean? This means that 95% of the time, the answer that we select from a random sample is going to sit in between those two. Okay, and that's what that means. We're going to actually continue on and visualize this with a picture. Okay, so let's suppose that you were to take 1,000 sample proportions of blue M&Ms. Now remember, this doesn't mean you're taking 1,000 M&Ms. What this means is you're taking a sample of size 50, you're figuring out the proportion of blues, you put a dot there, and then you do that experiment 1,000 times. Okay? So, where is 0.24 on the number line? Okay, that's what this wants us to do first. It says, plot the population proportion P equals 0.24. So where would it be? I'm going to use a red for this. So I put a dot there. That's 0.24. And we can see that that's the mean of the picture, right? Seems like that's right at the middle of this thing. Okay? It says draw the interval you computed above as a line segment. So remember, we're going from 0.12 until 0.36. So this is 0.12, this is 0.36. So I'm going to connect this with a line segment here. I'm going to connect like this. Okay, that's what we get. Okay. All right, so let's keep going. Next steps. Refining the empirical rule. If we use a normal curve to model the sampling distribution of sample proportions, we see a curve of similar center, shape, and spread to the dot plot above. Okay? The empirical rule tells us that approximately 95% of values are within 2 standard errors from the mean. If we wish to be more accurate, we can use the normal model to determine a more precise interval which contains 95% of sample proportions. Now, I know that in the past we've said that 2 standard deviations in either direction gives us 95% of everything, but that was actually a little bit of a cheating estimate. The real answer is closer to about 1.96, which you could see why we would round that to 2 because it's very close to 2, but we want to be a little more precise now. So what does this tell us? This tells us that if we go to the right by 1.96 standard errors, we go to the left 1.96 standard errors, this captures 95% of sample proportions. Okay? So this is what we need to know. When the criteria for approximate normality are satisfied, the normal model follows this rule. 95% of all sample proportions are within 1.96 standard errors of the population proportion. Okay, remember what sample proportions are, right? These are really the p-hats. And this is really p, right? So let's think about this. What this is saying is that 95% of all p-hats that you get are going to be within 1.96 standard errors of the p, right? And p is what you're looking for. That's what you want, right? You want the population proportion. Okay, let's move on. As a result of this fact, 95% of sample proportions have a deviation or error of less than 1.96 standard errors. We call 1.96 standard errors the margin of error. What is the margin of error? It's 1.96 times the standard error. So now we know where the margin of error comes from. If we know what the standard error is, we just need to multiply it by 1.96. If you multiply those, you get the margin of error. Now here's the problem, right? We normally have a formula. This is normally our formula, right? We have a p, and then we have 1 minus p, and then we divide it by n, right? What is the problem with just using this formula to get our standard error? The problem is we don't know p, right? We cannot calculate this formula because the whole point of this is that we're trying to figure out what p is close to. We don't have p. So this is why this next part is important. It says when p is unknown. We estimate the population proportion p because we don't know its value. For this reason, we must estimate the standard error using a sample proportion p hat in its place. So in other words, we cannot use this, so I'm going to cross it out. We cannot use this formula for the standard error. However, if we replace those p's with p hats, then that means we can actually use the formula. Again, this is an estimated standard error. You do p hat times 1 minus p hat divided by n, and then you take the square root of that. Okay. With this, the margin of error becomes, you just take that guy and you multiply it by 1.96. So that's where this formula comes from. We take 1.96 and multiply it by the square root of p hat times 1 minus p hat divided by n. Okay, you need to know. In the context of a confidence interval for an unknown population proportion p, the criteria for approximate normality are satisfied if the random sample includes at least 10 successes and 10 failures. If we are given the proportion of successes in the sample p hat, we can calculate the actual number of successes and failures by n times p hat and n times 1 minus p hat. Okay. All right, so the point of this is that we need to choose our sample size big enough so that we have 10 successes and 10 failures, right? And so if they give us a sample and they tell us what's in it, we just have to look inside and count to make sure that there's at least 10 successes and at least 10 that are not a success. Okay, let's keep going. In the previous examples, 24% of the M&Ms are blue, but let's pretend that we don't know that. I mean, if we were just doing an experiment to figure this out, we wouldn't know 24%, right? 24% is this population proportion P, which we are not aware of. But let's pretend we don't know that. We take a sample to estimate the proportion of M&Ms that are blue. Suppose you randomly select n equals 50 M&Ms and 16 of them are blue. Are the criteria for approximate normality of the sampling distribution met? Well, how many successes do we have in the sample? Let me back up here. Let me switch back to black, okay? So are the criteria for approximate normality met? Well, how many successes do we have in that sample? Well, it says that 16 of them are blue, so we have 16. What would the number of failures be in the sample? Well, we're just going to do 50 minus 16, right? Because if 16 of them are blue, then that means that 34 of them have to not be blue. And these are both bigger than 10. So, yes, the criteria for normality are met. Okay? When we ask you to show this on an exam or something, yes, you do need to write this down, okay? You need to show the two numbers and you need to say that they're both bigger than 10. This is how we know that you understand what this question is asking. Okay, so again, we are pretending that we're doing a brand new problem here. It says, suppose that you randomly select 50 M&Ms and 16 of them are blue. What is the sample proportion of M&Ms that are blue? Okay, so remember, you need to take the number of successes, so 16, and you need to divide it by the sample size, which is 50. 16 out of 50 of them are blue, right? So if you do that in your calculator and you divide that, you actually get 0.32. So that is p hat. Now we're going to compute the estimated standard error for this sample proportion. Let me remind you guys of that formula, right? We just learned it. The estimated standard error formula is right here. Okay, so that's what we're going to do with this problem. So I'm going to do, it's the square root of p hat, which is 0.32, 1 minus p hat, so 1 minus 0.32, and then we're going to divide it by 50. I'm not going to do this on the calculator in front of you guys because I already showed that many times in the previous lessons. So let me just do it on my calculator on my own. So when I plug this into my calculator, which I actually did just now, I get 0.06596969, but I'm going to round it to 3 decimal places, 0.066. So this would be the estimated standard error. Okay. All right, let's keep going. Compute the margin of error for 95% of sample proportions. Okay, so what is the margin of error? Again, remember, we take that number that we got up there and we're going to multiply it by 1.96, right? Because remember the formula here, let me remind you of it. The formula is right here now. The margin of error is we take the standard error and we multiply it by 1.96. Okay? Okay. So let's keep going. Again, this is, let me go back to where we were. We're on 6D, right? So what would this answer be? Now there are two ways of doing this, right? You can either take the answer from the last part and multiply it by 1.96, which I'm going to do. I'm just going to go ahead and multiply that because that's the easiest way to do it, right? We're going to take, it's going to be 1.96 times the standard error, right? So times the answer. So in other words, I'm taking this guy and I'm going to multiply it by 1.96. Okay. All right. So if I do that, I actually end up with 0.129. 0.129. There is something I want to point out, which if you, no, it's fine. So what I was going to say is that if you multiply, if you just do 1.96 times this guy, you'll get the same answer. Or you could just do 1.96 times that entire giant square root again. Either way, you'll get the same answer, right? Because again, these two are equal, right? So we get 0.129. All right, so let's move on. Now, understand that we have everything that we need to build the confidence interval, right? We have the p hat, which is 0.32, and then we have the margin of error, which is 0.129. So let's go to part E now. The upper and lower limits of the 95% confidence interval are p hat plus E and p hat minus E. Sometimes we write these as p hat plus or minus E. Compute these below. So we're going to do p hat minus E first. And then I'm also going to do p hat plus E. I'm going to do that one second. So let's start with p hat minus E. P hat is 0.32. So I'm going to do 0.32 minus 0.129. And then I'm also going to do 0.32 plus 0.129. So when I use my calculator, when I do 0.32 minus 0.129, I end up with 0.191. And if I do 0.32 plus 0.129, I end up with 0.449. So what we just found was the lower limit and the upper limit. So we could even call it right here. This is the lower limit, and this is the upper limit. Sometimes we write a confidence interval using interval notation. So interval notation looks like this. You put in parentheses and you put the smaller number, comma, and then you put the larger number. In math, when you write this in math, this means that we want all numbers in between those two numbers. And so this is what it looks like. We write 0.191 until 0.449, which we could put a 0 in front of the point. It does make it a little easier to read. So it's 0.191 until 0.449. Okay, that would be a confidence interval. Now I want you to notice also that this is for 3 decimal places. And some of you might be wondering, why did I choose to round it to 3 decimal places? Well, we didn't have to. We could have rounded these answers to 2 decimal places. So if we did that, it would be 0.19 and then 0.45, right? We rounded up because the next number is a 9. 449 rounds to 0.45. So this would be 2 decimal places. You know, again, if the problem doesn't tell you exactly how many decimal places to use, usually using 2 or 3 is safe, okay? It's never a bad thing to use 3. It's more accurate to use more decimal places. So 3 is usually good enough. Okay, let's look at number 7 then. It says, in the image below, the sampling distribution is centered at the population proportion. P equals 0.24, and an interval that extends a distance of E, which we computed above, to each side is shaded. Okay, so remember, 95% of all sample proportions are contained within this interval. Plot the sample proportion as a point, labeling it P hat on each of the number lines below. Okay, so where would we put P hat? Where would P hat go? So remember, our P hat was, let's recall, because I already forgot, it's 0.32, right? So where would 0.32 be? 0.32, if I want to use red to color that, 0.32 would be a little bit above, I guess it would be right here. So we want to label it P hat. In other words, that guy right there is our P hat. So this makes sense, right? I mean, we got 32% blue in this problem, right? But we know that that's higher than average, right? The average, the amount that that the real answer is there's 24% blue. But you do notice that it was within that margin of error, right? It is in the shaded part. Okay, so it says shade your confidence interval from E. It says on the bottom number line, shade your confidence interval from E. So let's go ahead and shade that then. Remember, our confidence interval is right here. We're going from 0.19 to 0.45. So from 0.19 to 0.45. 0.19 is basically right here. And then 0.45 is about right here. So this would be the confidence interval. Okay. It says shade your confidence interval from E. Oh, I forgot to put the P hat in there. Remember, P hat is 0.32. So this would be our P hat. And then this would be our P. All right, let's move on. Why are P and P hat contained in both intervals, whether we center the interval at P or P hat? So this is the crux of the question, right? So if we come back to here, we usually build, if you'll notice on the top part, we centered it at P, right? But on the bottom part, we did not center it at P. We centered it at P hat. And you notice that in either case, both intervals that we use contain the real answer P and also P hat. Another way to put this is if P hat is within the standard error of P, then that also means that P is going to be within the standard errors of P hat, right? In other words, if you are within 2 miles of your friend, that also means your friend is within 2 miles of you, right? Okay. So let's go ahead and answer this question. So since, well, let me again use black for this. Since P hat is within E of P, P is also within E of P hat. What is the big takeaway from what we're doing right now? The whole point of this is that if we center it at P hat, then we will most likely contain the real answer P. So the margin of error, adding that margin of error to and from P hat actually does contain the real answer most of the time. Okay? Centering the interval at the sample proportion. We have seen that 95% of sample proportions are within 1.96 standard errors. Remember, we call that the margin of error of the population proportion. Thus, for 95% of sample proportions, the distance to the population proportion is less than the margin of error. That means that if we center the interval at a sample proportion, it will contain the population proportion 95% of the time. So this gives us a name. We call this the 95% confidence interval. So this is important, guys. From now on, we are not just going to call it confidence intervals, but we need to be told how confident we want to be. So do we want to be 95% confident? We're going to see that we can actually contain many levels of confidence, and it just depends on how accurate we want our answer to be. Okay, so let's move on. It says you need to know the 95% confidence interval for a population proportion is P hat minus E, comma, P hat plus E, where E is equal to 1.96 times that square root. And remember, that square root, notice that these are hats in there now, P hats, because we're not going to have P. Okay? The criteria for approximate normality when we don't know P are that the sample must have at least 10 successes and 10 failures. That is, n times P hat is greater than or equal to 10, and n times 1 minus P hat is greater than or equal to 10. When the criteria for approximate normality are met, about 95% of such intervals will contain the population proportion P. Okay? So what this means is that if you were to calculate a confidence interval and you get a random sample and you get a confidence interval from that, 95% of the time your confidence interval will contain the correct answer in there. Of course, 5% of the time it could be wrong, right? Or 5% of the time it'll be wrong, but that is a risk we have to be willing to take, right? We're never going to know with 100% accuracy unless we count every single M&M in the world or every person in the world. So that's what statistics is for, is to get us reasonably accurate results. Okay, next steps. Tabulated below are amounts of blue M&Ms from 40 random samples of M&Ms, each of size n equals 50. Okay, so for example, let me just show you what these mean, right? For example, the first one says, let's say we got a sample, and out of the 50 M&Ms, 8 of them were blue. That's what this first sample means. Or for example, sample number 18, out of 50 M&Ms, 9 of them are blue. Or let's look at a high-end one, right? Or something that's a little bit higher. For sample number 27, 16 of them are blue, right? Or sample number 29, 17 of them were blue. We're about to compute up to 40 confidence intervals for the population proportion of M&Ms that are blue. That is a lot of work. So we're not actually going to do this 40 times. If we were in a class, I would have all of you do one of these, and then we would get our answers all put together. Okay? So we just did a problem, right? And we got a confidence interval. Let's look at the confidence interval. Remember, we went from 0.19 to 0.45. And so I'm going to put that here on our picture because it's asking us to do that. So 0.19. Oh, you know what? Let me go ahead and get red here. 0.19 to 0.45. The population proportion of M&Ms that are blue is actually 0.24. Let's plot this as a point on the number line. Does the confidence interval contain the population proportion? Well, let's go ahead and put the real answer. Remember, the real answer is 0.24. The real answer is right here. So is it inside? The answer is yes. Right? So does the confidence interval contain the population proportion? And we'll say yes. 0.24 is contained. In the confidence interval. There are many more confidence intervals to compute. To speed things up, your instructor will assign one of the remaining samples above to you. Once you have it, answer the following questions. So, okay, I'm going to do this on my own, and I recommend that you try it on your own to see if you can work through one of these samples. So you're going to choose any one of these samples here, and you're going to work it out on your own just to make sure that you understand how to do it. But I'm going to do one myself. I'm going to go ahead and pick one at random. How about I pick... Let's go with this one. Why not? Okay, I'm going to go with number 34. Let's suppose that there are 50 M&Ms and 14 of them are blue. And remember, these are randomly selected. In other words, I just chose a random bag of 50 M&Ms, and inside of that bag were 14 blues. So how many blue M&Ms are in your sample? So 14. Okay. What is the sample proportion from this sample of size 50? So to calculate your p-hat, you just have to take your number of blues and divide it by the total sample size. So if we put this in our calculator, we get 0.28. Now we're going to compute the margin of error for a 95% confidence interval. So how do you find the margin of error? Remember, you're going to do 1.96 times that square root. So it's going to be 1.96 times the square root of, I'm going to put 0.28 times 1 minus 0.28 divided by 50. There's two ways of doing this. Again, you could do just the square root part, get your answer, and then multiply it by 1.96. Or you can do the entire thing on your calculator, okay? So let me just demonstrate the calculator. So I want to demonstrate how to do this on an actual calculator. So we're going to put that guy in our calculator. So I have 1.96, and then I'm going to do times, and then I'm going to do that square root, right? So second square root, and then it's going to be 0.28 times 1 minus 0.28, close parentheses, and then I'm going to do divided by 50. And if I hit enter, I get my margin of error, right? My margin of error is 0.1244. So if I round that to 3 decimal places, that's 0.124, right? So let's go ahead and write our answer down here. I have 0.124. Or if we wanted to round it to 2 decimal places, we could. It's 0.12. Okay, so now we know where those answers come from, and let's keep going here. So now we just need to subtract and add the margin of error from p hat. So let's do p hat minus e, and we're going to do p hat plus e. If we do p hat minus e, we get 0.28 minus 0.124. And then this one's going to be 0.28 plus 0.124. So I'm going to go ahead and do that in my calculator. So 0.28 minus 0.124 is 0.156. And then 0.28 plus 0.124 is 0.404. And so my confidence interval is from 0.156 to 0.404. Okay. Or if I wanted to write this with only 2 decimal places, I can round it to 0.16 and 0.40. Again, because the 5 rounds up when there's a 6 afterwards, and the 0 rounds down or stays as a 0 when there's a 4 afterwards, right? So this is the confidence interval that we got for sample. Remember, I chose sample number 34. If you do this with different samples, every sample is going to give you a different confidence interval. Okay, so it says, plot your confidence interval on the number line below as a line drawn between the interval's lower and upper limits, and also put the 0.24 in there. Does your interval contain the population proportion? Okay, I'm going to do this in red. So I'm going to go from 0.16, which is something like right here, and that's going to go until 0.40, which is right here. So it looks like that. And where is 0.24? 0.24 is something like right here. This is P, right? So does it contain P? It sure does. So yes, P is contained in the confidence interval. Now, this next question, we can't really answer it because we don't have a whole class of you to do this. But here's the idea. The idea is not all of them are going to contain the real answer, right? Because we know that it's 95% accurate, which means most of them will, but it's possible that a few of those up there will not. Okay, but do several of them and you'll see that most of them are going to contain P. So let's just go ahead and answer this question here. So we don't actually have the answer for this part. So you guys are going to have to take my word for this part. But if you actually do work it out from all of those samples above, in other words, what I'm saying is there are 40 of them here, right? There are 40 different samples. And so if you do it with all 40 samples, you'll actually see that all of them except for 2 contain it. So how many of the intervals contain the population proportion? So 38 contain it. What percent of the intervals can contain the population proportion? Well, guess what? If you do 38 divided by 40, you get exactly 95%. Okay? So what does it mean when we call such an interval a 95% confidence interval? So it means 95% of all confidence intervals contain the population proportion, P. So this is important. This is a sentence that we're going to be writing a lot, okay? When interpreting a 95% confidence interval for a population proportion, we usually say that we are 95% confident that the population proportion falls within the interval. Let me highlight this because it's so important, okay? This sentence, we are 95% confident that the population proportion falls within that interval. We're going to be writing that quite a bit, okay? Because whenever we find a confidence interval, we're going to interpret it. And we have to write down what these things mean in English. So that is the form that your sentence is going to take. Again, what we mean by 95% confident is that such intervals contain the population proportion for about 95% of samples. Okay? And that is it. This is the end of our lesson. And so the code word, the code word for this lesson is confidence. Okay, confidence. All right, guys, thank you very much for watching and hope that video was helpful.